Did you catch that? That dramatic shift. One moment, everything's crisp and clear. The next, just a sort of chaotic mess.
Yeah.
It's almost as if the space itself, dictates how we hear, how we perceive sound, how we experience it.
It absolutely does. That's the fascinating truth.
Welcome to the Deep Dive. Today, we are truly plunging headfirst into an area that, well, it's often overlooked, but it subtly shapes nearly every moment of our daily lives. We're talking about architectural acoustics. We've pulled together a fantastic collection of source materials for this one, really giving us a true deep dive into the science and the art of sound within our built environment.
Yeah, think of it like uncovering the invisible architecture of sound. It's really neat stuff.
Exactly.
And our mission for you, the listener, today is really to pull out the most impactful insights from these sources. We're going to try and take what might seem like incredibly complex physics and engineering concepts,
Right.
and distill them down into clear, actionable knowledge, stuff about how sound works in the spaces you inhabit every single day.
And why it matters.
And crucially, why it matters so profoundly for our comfort, our communication, our overall well-being. By the end of this deep dive, you'll gain an entirely new appreciation, I think, for the unseen forces that sculpt our auditory world.
That's a wonderful way to put it. It really is this incredible blend, isn't it? Art and science, where so much meticulous thought goes into something we constantly take for granted, just the way sound behaves around us.
We really do.
I found it particularly captivating digging into this, just how designers manipulate sound, aiming for that optimal human experience, shaping everything from like the clarity of a whispered conversation to the sheer grandeur of a symphony. So we're going to cover everything, from the very nature of sound itself right down to how designers masterfully control it.
Okay.
So to really deep dive into this properly, we first need to get on the same page. What is architectural acoustics, actually?
Good starting point.
Our source materials give us a wonderfully concise definition to start with. They define architectural acoustics as the art and technique of designing spaces, structures, and mechanical systems to meet hearing needs.
Right. That phrase art and technique really stands out, doesn't it?
It does. It immediately tells you this isn't just about, crunching numbers or applying abstract physics equations, although obviously that's foundational.
Sure, it has to be.
But this discipline, it seems deeply rooted in understanding human perception, psychology even, how we experience sound, how it affects our mood, our ability to concentrate.
Our relationships even.
Exactly. It's about creative problem solving to get to a desired auditory outcome. Essentially crafting an experience within a measurable environment.
It's not just controlling sound, is it? It's more like sculpting silence, enhancing presence.
Yeah, creating that sort of invisible comfort zone, something that impacts how we connect, how we learn, even how we heal, and often without us ever realizing it's happening.
Right, that subtlety is key.
And the scope.
Yeah.
The scope of this field is way more expansive than you might initially imagine. Our sources say it covers everything which concerns hearing in and around buildings.
So not just inside the room.
No, exactly. It extends to external factors, too, like traffic noise from a nearby highway, or the rumble of a subway train beneath your feet.
Or even planes flying overhead.
Right. It deals with mitigating all that unwanted noise, but also with ensuring those desired auditory experiences, like the clarity of a lecture in a big university hall, or that rich, enveloping sound in a concert venue.
It's a holistic approach then, looking at sound in our whole built environment, every possible input and output.
Precisely. And what's truly crucial here, and our sources really emphasize this, is the absolute necessity of integrating sound control with other building functions.
Yes. This is vital.
This isn't some isolated discipline you just, tack on at the end like decorative trim. It has to harmonize intimately with structural integrity, with aesthetics.
Because nobody wants an acoustically perfect room that looks like a padded cell.
Right. And with lighting, ventilation systems, even how people move through a space. You mentioned this earlier, the crucial aspect of integrating acoustics from day one. Why is that so vital? What are the practical consequences if you just treat acoustics as an afterthought?
Oh, that's an absolutely critical question. And frankly, it's a common pitfall in design, unfortunately. If you treat acoustics as an afterthought, you often end up with compromises that are, well, incredibly expensive to fix.
Right.
And sometimes they're fundamentally unfixable, or at least not without major disruption. Trying to retrofit proper sound insulation or, say, redesign airflow for quiet operation into an already finished building. It's like trying to fix the plumbing in a completed skyscraper.
Yeah, sounds like a nightmare.
It's prohibitively complex, it often compromises the building's aesthetic vision, and it costs a fortune. The real insight here, I think, is that acoustics is truly the invisible structural beam of human experience in a building.
I like that analogy.
Neglecting it early on leads to what we could call architectural regret. Those initial design choices, the building's overall layout, the placement of rooms, selecting construction materials, even just routing the ductwork, they all have massive downstream effects on how sound will behave.
So thinking about it from the very beginning allows designers to just sort of bake in optimal performance, seamlessly and cost-effectively.
Exactly. Ensuring a comfortable and functional space from day one, rather than trying to patch up problems later.
Makes sense.
And to build on that, our sources offer a second complementary definition, which I think further refines our understanding. Architectural acoustics is also the art and science of designing a room or building that ensures both comfort and communications, and provides special features as to purpose and use of the building.
Okay, so this one really zeroes in on the human-centric aspects.
Precisely. Let's unpack what comfort and communications mean in an acoustic sense. Think about a poorly designed space, right? You might experience significant auditory discomfort, strain, maybe, constantly struggling to hear over background noise.
Oh, yeah. Leads to fatigue, stress, frustration, definitely.
Imagine trying to have a private conversation in one of those big echoey restaurants. You find yourself shouting just to be heard, and then you feel hoarse by dessert.
Been there. Or trying to focus in an open-plan office where every single phone call and conversation from 20 feet away is perfectly clear.
That's acoustic discomfort, and it directly impacts productivity, well-being, everything. Conversely, good acoustics facilitates clear communication.
Right, so in a classroom, every student can clearly understand the teacher.
Exactly. Or in a collaborative office, teams can brainstorm effectively without constant distractions. And in a performance hall, it means every note, every word is delivered with pristine clarity and emotional impact to every single seat. It fosters a truly immersive experience.
Okay, and what about the second part of that definition, the special features as to purpose and use?
This is where the custom-tailored nature of acoustic design really shines. It adapts to the specific demands of a space. A concert hall, for example, needs very precise reverberation times.
Reverberation times, that's how long sound lingers, right?
Exactly. You need it for musical notes to sort of bloom and blend harmoniously. You want the sound to be rich and full, not dry and dead.
Okay.
A library, on the other hand, needs pretty much the opposite. Quiet zones, high sound absorption, minimal sound leaking between reading areas to support focus.
Right. Total concentration.
Think about recording studios, too. They demand extremely low background noise and very specific room characteristics for accurate mixing. Or even a gymnasium, often super reverberant because of all the hard surfaces. That makes speech intelligibility a real challenge for announcements.
And factories. Must be a nightmare with machinery noise.
Huge challenge. Factories need robust noise containment, isolation strategies not just to protect workers' hearing, but also to stop noise pollution spilling out into the neighborhood. So the acoustical design shifts dramatically based on the building's main function. It shows the incredible versatility needed in this field.
Wow. So if we kind of connect all this back, both definitions really emphasize that architectural acoustics is this sophisticated blend of technical knowledge, the physics, the materials science, and creative application, but it's all ultimately aimed at enhancing the human experience within our built environments.
Yeah, making spaces work for us, not against us, audibly speaking. Creating environments that support what we do and how we feel, often without us consciously noticing the intricate design work behind it.
Okay, so once we have that foundational understanding of what architectural acoustics is and why it's so vital to integrate early, the next natural question is, what are its core objectives? What's a designer actually trying to achieve?
Right. What are the goals?
Our sources lay out three main objectives. I think of them as the fundamental challenges or maybe the pillars that any acoustical designer has to address.
Okay.
The first objective is about controlling echoes and securing the best distribution of sound. Now, we've all been there, right? That empty room or a big hall with hard surfaces where every clap just bounces back at you.
That annoying echo.
Yeah.
Why are echoes problematic? Well, they severely reduce clarity, intelligibility. If you're in a really reflective room, a sound hits your ears, then bounces off a hard surface, and you hear it again, just slightly later.
And that delayed reflection overlaps with the next sound,
making everything muddy and indistinct, like trying to listen to someone speak with a permanent delay pedal on their voice.
Yeah. not ideal. So controlling those reflections is paramount for clear communication and just pleasant listening.
But it's not just about eliminating echoes, is it? It's also about securing the best distribution of sound.
Right. Making sure the wanted sound, a speaker's voice, music, whatever, reaches everyone in the space clearly and evenly at the right loudness.
Yeah, you don't want those dead spots where the sound just fades out, or hot spots where it's blasting you.
Exactly.
Our sources mention two key methods for achieving this. First, the study of the shape of the room.
Room geometry is huge.
And second, the estimation of the amount of sound-absorbing material needed.
Nidarial selection, yeah. So what about room shapes? Are some naturally better or worse?
Oh, definitely. Large parallel walls, for instance, they can create problematic flutter echo sound bouncing back and forth, or standing waves, creating zones of really high and low sound pressure.
Okay. So non-parallel surfaces are better. Angled walls, convex shapes maybe?
Yeah, those can help scatter sound reflections, spread the energy more evenly, and then you bring in the materials, soft furnishings, thick carpets, those specialized acoustic panels.
The ones made of porous stuff like mineral wool or fiberglass?
Right. They work by converting sound energy into a tiny amount of heat through friction. They basically soak up the sound reflections, stop the echoes.
So imagine walking into a big lecture hall and the speaker's voice, even without a microphone, is perfectly clear in every single seat, front to back.
That's the goal, an effortless learning experience. Or a music venue where every note, every nuance sounds crisp and balanced no matter where you are.
That's good sound distribution and echo control just working its magic silently.
Exactly. Now, building on that, the second objective shifts our focus a bit, from within a single room to the challenge of managing sound between rooms.
Ah, keeping sound where it belongs.
Precisely. This objective is about reducing sound from one room to another through proper insulation. Super important for privacy, for focus, just for minimizing distractions in adjacent spaces.
We all want a quiet office to concentrate, or a peaceful bedroom at night without hearing the neighbors.
Absolutely. If sound travels easily between rooms, those basic goals just become impossible.
So what does proper insulation really mean? It's not just building a thick wall, is it?
Not entirely, no. It involves understanding concepts like mass, decoupling, and crucially, sealing gaps. Those are the fundamentals of sound isolation.
Okay, mass makes sense. Heavier, denser walls block sound better, like concrete or multiple layers of drywall.
Right. They offer more resistance to the sound waves trying to push through.
Yeah.
Then there's decoupling. That means physically separating layers, like walls or floors, so vibrations can't easily jump directly from one side to the other.
How do you do that? Special clips? Air gaps?
Yeah, things like resilient clips or channels for mounting drywall, creating air gaps inside walls, sometimes even building double stud walls with two separate frames. It's all about breaking that direct path for the sound vibrations.
And then you mentioned ceiling gaps. You said a tiny gap can be worse than a thin wall. Why is that?
It's because sound, much like water, will always find the path of least resistance. Even a tiny crack around a door frame, an unsealed electrical outlet, a small hole for a pipe, a gap above a wall in the ceiling space. Any little gap can drastically undermine the sound isolation of the whole wall or floor.
Wow, so it's really about meticulous attention to detail.
It really is. Understanding those specific pathways sound takes. Think about the difference between a well-designed, quiet office building where you can actually concentrate and have private conversations.
Versus a cheap hotel where you hear everything from next door.
Exactly. That's the profound difference proper inter-room sound reduction makes.
Okay, that's clear. So what's the third objective?
The third one is about isolating machines and other noise-producing equipment.
Ah, the mechanical noise. HVAC, elevators.
Plumbing, industrial machinery, even just your washing machine at home. This is critical across a huge range of settings: residential, commercial, hospitals, industrial plants.
Because if that equipment isn't properly isolated, its noise and vibration can just permeate the whole building, right?
Really, leading to constant annoyance, fatigue, reduced productivity, even long-term health issues like stress or hearing damage if it's loud enough.
So how do designers achieve this isolation in practice?
It's usually a multi-pronged approach tailored to the specific noise and equipment. One common method is vibration dampening, using special resilient mounts, pads, spring isolators, things that absorb the vibrations from the equipment before they get into the building structure.
Like shock absorbers for machines?
Kinda, yeah. For really big stuff like generators or chillers, you might even need separate floating foundations. physically decoupled from the main building structure to stop vibrations traveling through the ground or floor slabs. Then you have enclosed rooms, basically soundproof boxes, built around noisy machinery, often using high-mass materials, and lined with acoustic absorption inside to trap the sound.
And for things like HVAC systems.
Designers might use duct silencers. They have internal baffles that absorb noise inside the duct, or they carefully design the duct layout itself to minimize noise transmission. Acoustic barriers like thick walls or enclosures are also used to block airborne noise.
Think about a hospital. It needs to be quiet for patients to recover, for staff to concentrate, but it's full of essential machinery.
Exactly. Good acoustic design makes sure those machines operate silently, almost invisibly, creating a healing, focused atmosphere. Or think about a quiet apartment building where you're blissfully unaware of the boiler room hum downstairs or the elevator right next to your bedroom.
That's the quiet comfort achieved through careful isolation.
Precisely. So if we synthesize these three objectives, controlling echoes and sound within a space, reducing sound between spaces, and isolating noisy equipment, they all point towards a single overarching goal. As our source stated, to allow wanted sound to be heard properly and to mask unwanted sound to a point where it does not cause annoyance.
Okay, wanted versus unwanted. That sounds pretty key. But isn't that subjective?
Profoundly subjective and entirely contextual. That booming bass and vibrant music in a nightclub, absolutely wanted for the patrons inside. Integral to the experience.
But the same sound, same intensity heard in the apartment next door at 3 a.m.
Definitely unwanted, a source of major annoyance. Or think about the quiet hum of a ventilation system. In a factory, maybe it's acceptable background noise. In a concert hall during a quiet piano solo, it becomes a distinct unwanted distraction.
So acoustic design isn't just about making things silent, it's about optimizing the sound environment for its specific purpose.
Exactly, for the activities and the people within it.
Right.
Which leads us to what I think is the golden rule in architectural acoustics, something clearly stated in our source material. It is essential for a designer to integrate the acoustical objectives in the early stages of the architectural design process.
Back to that early integration again, why is it so crucial?
Because acoustics needs to be there at the drawing board, not an afterthought during construction. Trying to retrofit proper sound blocking walls or redesign HVAC for quietness or install vibration isolation after a building is designed or even built, it's almost always far more expensive.
Right.
Significantly less effective and incredibly complex. Often requires tearing things down. It's the difference between proactive, seamless design and reactive, costly, often compromised fixes.
So those initial choices, layout, room placement, materials, even windows and doors, they all have huge downstream effects on sound.
Massive effects. Considering acoustics from the very beginning lets designers bake in optimal performance seamlessly, cost-effectively. It avoids that architectural regret and leads to spaces that truly support human comfort and communication.
Okay, that makes perfect sense. So we've talked about what architectural acoustics is, why it's fundamental, what its goals are, but none of that fully clicks unless we understand what we're actually trying to control, sound itself.
Right, the fundamentals.
Our sources give a few different definitions, each offering a slightly different perspective, which helps build a fuller picture.
Okay.
First up, the oscillation in pressure of the atmosphere, which is capable of being detected by the human ear.
That really nails the physical aspect, doesn't it? Air molecules being compressed and expanded, tiny invisible pressure waves.
And it grounds it in human perception. It's only sound for us if our ears can pick it up. Emphasizes that biological connection.
Then there's a second definition, sound as a form of energy propagated in waves, which continues to subsist until filtered through a material turning into heat by friction.
This one highlights the energy aspect. It's energy in motion, traveling outwards until it eventually loses that energy, often turning into a tiny amount of heat.
Exactly. Think of a sound wave hitting a heavy curtain. Some of that sound energy literally transforms into a minuscule bit of warmth in the fabric. It gets absorbed and dissipated.
Fascinating. And the third definition.
This one brings it back to our subjective experience. The sensation produced through the ear, resulting from fluctuations in the pressure of the air.
So sound isn't just a physical wave or energy, it's a sensation. What our brain interprets from those pressure changes.
Right. Without a receiver, the physical energy might exist, but there's no sound as we experience it. So these definitions really complement each other, don't they? Moving from the physical phenomenon to its energy properties and finally to how we actually perceive it.
They do. So building on that, our sources break down how sound is heard into 3 essential elements. Always required. You can't have perceived sound without all 3.
The magic triangle. source, medium, and receiver.
Let's start with the source of sound, defined as normally a vibrating body, which converts some other form of energy into vibration.
Makes sense. When you speak, your vocal cords vibrate. A guitar string vibrates. A speaker cone vibrates.
Even a dropped tool, it vibrates. It's taking some other energy, mechanical, electrical, whatever, and turning it into vibration.
The very start of the sound, and a crucial point highlighted here. The source can be made quieter.
Often the first and maybe best place to intervene for noise control?
Absolutely. If you can quiet the source, you've tackled a huge part of the problem before the sound even gets going. The sources also mentioned transducers.
Right, devices that convert energy forms.
Exactly. Loudspeakers convert electrical energy to sound. Microphones do the opposite, sound to electrical. Perfect examples of this energy conversion principle at work.
Okay, so once you have a source vibrating, you need the second element, a transmission path, or medium, defined as any substance that allows the vibration to be transmitted in the form of a wave motion.
This is critical. Sound needs a medium. It can't travel in a vacuum because there are no particles to vibrate. The medium carries the energy from the source to the receiver.
And just like the source, the path can be influenced. The transmission can be made to transmit more or less sound.
Yeah, this is where architectural acoustic design really gets involved. Guiding sound where you want to, like in an auditorium, or blocking it where you don't, like between apartments.
And our sources break down transmission into two main types, right? This distinction seems really important for designers.
Hugely important, because the fixes are different. First, you have airborne sounds.
That's what we usually think of. Speech, music, traffic noise, transmitted through the air.
Exactly. Air is the most common medium for us. But then you have structure-borne sounds.
The sounds traveling through solid stuff, walls, floors, the building frame.
Right, like hearing footsteps from upstairs, or feeling the hum of machinery through the floor, or the rumble of a washing machine. Yeah.
And the strategies to deal with those are different. Absorbing panels for airborne, maybe, but something else for structure-borne.
Generally, yes. Structure-borne noise often needs vibration isolation, floating floors, physically decoupling elements. Airborne noise might rely more on absorption, mass, and ceiling gaps. Understanding that difference is key to solving acoustic problems effectively.
Got it. So we have a source, medium. What's the third element?
The third essential element for sound to be heard is the receiver. Our sources simply define this as the human ear.
Or some other sensor like a microphone.
Right. Without an ear, or something capable of interpreting those vibrations, the physical phenomenon might exist, but it wouldn't be heard or perceived in the way we understand it.
And the fascinating part here you mentioned is that the receiver can be influenced.
Yes. This opens up the whole world of psychoacoustics, how psychological factors affect our perception of sound.
How so?
Well, our perception of loudness or annoyance or even pitch can be altered by our mood, our expectations, even what we see. Think about loud music exhilarating at a concert, maybe.
But infuriating from your neighbor's apartment. Same sound, different perception.
Exactly. And more directly, things like earplugs or noise-canceling headphones actively influence the sound the ear receives. They reduce intensity or cancel specific frequencies.
So this is the aha moment for the listener, realizing that our own ears and how we interact with sound are part of the equation too.
Absolutely. It's not just about the source and the path. It's profoundly about how you perceive it. It's an active system.
Okay, so when we talk about sound, it's not all the same. Our brains process different types differently. Our sources classify sound into two broad categories, ordered and disordered.
A useful distinction for the acoustician's goals.
Right. Music is defined as sounds organized to have melody, rhythm, harmony, and dynamics. Clearly ordered, it has structure, intention, pattern, designed to evoke emotion.
Aesthetic form, yeah.
Similarly, speech, defined as to express with the voice, also ordered. It has linguistic structure, patterns, intentional communication, meant to convey meaning. On the other hand, you have noise, defined as sound, especially of the loud and harsh kind, classified as disordered sound. The example given is street noise.
Lacks a discernible pattern, often unpredictable, unwanted, disruptive, doesn't usually convey useful information.
Exactly. So when we think about architectural acoustics, a big goal is enhancing those ordered sounds, clearer music, more intelligible speech, while mitigating or masking the disordered ones.
Reducing their intensity, blocking them, or sometimes even using another sound, like gentle white noise, to make the unwanted noise less noticeable, creating an auditory hierarchy.
Letting the desired sounds shine through. Okay.
Now, let's maybe dig a bit deeper into the science of how sound waves actually work. It's crucial for understanding how they interact with buildings.
The physics bit.
Right. Our sources explain that sound waves are longitudinal wave motion with which sound energy travels through a medium. What does longitudinal wave motion actually mean?
Like a slinky. You push one end, the compression travels down, but each coil just moves back and forth.
Perfect analogy. The particles of the medium vibrate parallel to the direction the sound energy is moving, pushing and pulling their neighbors. That's why sound needs particles. It's different from light waves.
And the fascinating thing is, the energy travels, but the material itself doesn't go with it.
Exactly. It carries energy away from the source without carrying the material itself with it. Think of ripples on a pond. The energy spreads out, but the water mostly just moves up and down. Air molecules do the same with sound: vibrate, pass the energy on, return to their spot. The air doesn't blow across the room with the sound.
Okay.
And the sources reiterate. Sound waves are mechanical. Unlike electromagnetic waves, they require vibrations of their medium's molecules or particles. This is fundamental. Unlike light, sound needs a physical medium, air, water, a wall, for its molecules to vibrate and transmit the energy.
Which leads directly to that classic aha moment.
Well, that is why sound cannot travel through a vacuum. No particles, no vibration, no sound transmission. It's a direct consequence of its mechanical nature. You can't soundproof space by creating a vacuum between walls. Not practically, anyway.
Right. So when we study these waves, there are 4 fundamental measurements our sources highlight, the basic building blocks for acousticians.
The ways we quantify them.
First, a cycle, defined as a full circuit by the particle, that single back and forth oscillation.
Yep. Push forward, pull back past rest, then return to the start. One complete vibration.
Then building on that, frequency, number of complete cycles per second measured in hertz. This is what we perceive as pitch.
Exactly. More cycles per second, faster vibration, higher frequency, higher pitch. A high violin note versus a low bass drum.
Got it. Next is amplitude. Maximum displacement of a particle to either side of its normal position during vibration. How far it swings.
Right. A bigger swing means more energy, which relates directly to the intensity or loudness. Shouting makes particles swing further than whispering. Higher amplitude, louder sound.
Okay. And finally, period. The time required for one complete vibration measured in seconds per cycle. It's just the inverse of frequency.
Basically, yeah. High frequency means a very short period for each cycle. Understanding these measurements, cycle, frequency, amplitude, period, lets designers analyze and predict sound behavior precisely, linking the microscopic particle vibration to our macroscopic experience of hearing.
So they can choose materials or shapes to target specific pitches or loudness levels?
Exactly.
Okay, so we've got a handle on what sound is fundamentally and how it travels. Let's talk about its measurable properties, the characteristics that let designers quantify the invisible and predict sound behavior.
Turning physics into design tools.
Our sources list 7 key properties: speed or velocity, frequency or pitch tone, power, intensity, loudness, sound pressure, threshold of audibility, threshold of pain, and directionality of sound sources. Let's dig into the ones where the sources give us specifics.
Sounds good. Let's start with speed or velocity. The sources give a baseline. Sound travels at 330 meters per second at normal temperature, 20 degrees centigrade.
Which is about 738 miles per hour. Fast, but way slower than light, hence lightning before thunder.
Right, and what's interesting is how the medium affects this speed. Sound travels faster in denser media. It goes much faster in liquids and solids than it does in air.
So that explains why structure-borne sound travels so well through buildings, through concrete or steel.
Absolutely. Sound travels through steel nearly 15 times faster than air. That's why vibrations from machinery or footsteps can propagate so quickly and effectively through a building's frame.
And temperature matters too. Sound travels faster through air at 30 degrees C than at negative 17 degrees C. Warmer air means faster sound.
Slightly faster, yes. It has subtle but real implications for sound over long distances or in spaces with big temperature differences, like large venues or outdoors. Affects timing and clarity.
Okay. Property number 2, frequency, which we relate to pitch. The higher the frequency, the higher the pitch, and vice versa. High note, high frequency, low note, low frequency. Simple enough.
Measured as number of vibrations in cycles per second, also known as hertz. So 1,000 cycles per second is 1,000 hertz, or 1 kilohertz, allows designers to target specific frequency ranges.
And the range of human hearing is huge, 20 to 20,000 hertz. From deep rumbles to piercing highs, though that range shrinks with age, right? Especially the high end.
That's typical, yes. But what's really critical for acoustics, and a key insight from the sources, is that Humans are most sensitive to sounds with frequency at 500 to 4,000 hertz,
And why that range specifically?
because that's where most human speech frequencies fall. Our ears evolved to be incredibly sensitive right there. Makes perfect sense for communication and survival.
Which links directly back to that core objective, facilitating clear communication. If a space muffle sounds in that critical 500, 4,000 hertz range, it fails a vital human need.
Precisely. Whether it's a classroom, an office, a public announcement system, clarity in that range is paramount.
Okay. Property 3, power, also known as intensity or loudness. A sound's intensity is its loudness or pressure against the eardrum, measured in decibels, dB.
The decibel, the unit we use constantly to talk about noise levels, understanding it is crucial.
And the scale itself is kind of tricky, right? The sources say the decibel scale is a relative logarithmic scale in which 0 dB represents the threshold of perfect human hearing. Why logarithmic?
Because the range of sound intensities we can hear is absolutely enormous. The loudest sound we can tolerate is trillions of times more powerful than the quietest we can detect. A linear scale would be unmanageable numbers with dozens of zeros.
So the logarithmic scale compresses that vast range into usable numbers.
Elegantly, yes.
Yeah.
And 0 dB isn't absolute silence. It's the quietest sound a young, healthy ear can typically perceive. An incredibly faint sound pressure fluctuation.
But here's the really counterintuitive part. An increase in 3 dB represents a doubling of sound intensity. Only 3 dB doubles the power.
That's the key aha moment. Let me repeat that. Just a 3 dB increase means the sound is twice as powerful. So seemingly small decibel changes represent very significant changes in sound energy and often a noticeable difference in perceived loudness.
So going from 60 dB to 63 dB, while maybe not sounding massively different, is actually double the intensity.
Literally double the physical sound intensity. That's why acousticians pay such close attention to even small dB changes. They add up fast and profoundly impact perceived noise and comfort. Explains why adding just one more noisy machine or having two conversations instead of one can feel like a much bigger jump in noise.
Okay. The sources give some real-world examples measured 1.2 meters away. A whisper is about 15 dB.
Very quiet.
Normal speech is around 60 dB.
A common baseline.
Loud talking is 75 dB, and shouting hits 90 dB.
Now let's apply that 3 dB rule. The difference between normal speech, 60 dB, and shouting, 90 dB, is 30 dBs.
Okay.
Since every 3 dB doubles the intensity, a 30 dB difference means the intensity has doubled 10 times. 30 divided by 3 is 10.
Wow, 10 doublings.
That's 2 times 2 times 2, 10 times. Over 1,000 times more intense than normal speech.
That really illustrates the power of the decibel scale, and why small dB reductions from good acoustic design can make such a huge difference to comfort.
Absolutely. It quantifies those dramatic changes effectively.
Okay, so the sources list a few other important properties, even if there's less detail provided. Concepts that acousticians work with all the time.
Right, rounding out the picture.
There's sound pressure, closely related to intensity and loudness, you said. It's the force the waves exert.
Yeah, on surfaces like your eardrum or a wall. Measuring sound pressure helps predict impact on structures, vibrations, and hearing health. Designers use it to choose wall thickness, window types, things like that.
Then the threshold of audibility, that's the 0 dB baseline we talked about. The quietest sound we can hear.
For a young, healthy ear, yes. Getting below certain thresholds for unwanted noise in places like recording studios or labs is a major design challenge. Meticulous work.
And at the other end, the threshold of pain. The upper limit where sound becomes uncomfortable or damaging.
Around 120, 130 dB typically. Hugely important for health and safety design in noisy environments like factories or concerts, preventing pain and hearing damage.
And finally, directionality of sound sources. Sound doesn't always spread out equally.
No. Many sources, like a person speaking or a trumpet or most loudspeakers, project sound more strongly in one direction, especially higher frequencies. Think of a megaphone focusing sound.
So understanding that helps place speakers correctly in an auditorium, for example. Directing sound where it's wanted, keeping it away from where it's not.
Exactly. It influences the design of reflectors, diffusers, how sound energy moves in a space. So what does this all boil down to? Understanding all these properties lets designers precisely measure, predict, and manipulate sound, turning this invisible, often chaotic thing into a tangible design element that massively impacts our experience of the world.
We have certainly covered a tremendous amount of ground today on the deep dive. We started by unpacking the core definitions of architectural acoustics, seeing it as both art and science, dedicated to our hearing needs in built spaces.
Right, that blend is key.
We looked at its huge scope, from inside sound to outside noise, and really hit home the critical need for integrating acoustics early in design to avoid that architectural regret.
A costly mistake to make.
Then we dove into the three main objectives: controlling echoes and distributing sound evenly within a space,
Getting the sound right inside the room.
reducing sound transmission between rooms for privacy and focus,
Keeping sounds separate.
and diligently isolating noisy machinery for comfort and well-being.
Managing the mechanical noise.
Yeah.
And we didn't stop there. We stripped sound down to its fundamentals, understanding it as pressure oscillations, a form of energy, and a sensation, always needing that source, medium, and receiver.
Yeah.
We explored the nature of sound waves, those longitudinal mechanical waves carrying energy, not material, and why they absolutely need a medium, why they can't travel in a vacuum.
Right. And finally, we quantified the invisible, talking about cycle, frequency, amplitude, period, and delving into those measurable properties: speed, pitch, and especially power or intensity on that logarithmic decibel scale.
Yeah. Remembering that crucial 3 dB doubling.
Definitely.
So, if we connect this all back to the listener, you now have, hopefully, a foundational understanding for just how much intentional, meticulous design goes into the sounds you encounter every single day.
Yeah, that clarity of conversation in the office, the quiet of a library, the impact of a concert.
Or even the subtle hum you don't hear from the building's HVAC system. All of that is thanks to the careful application of these principles of architectural acoustics.
It really is a silent design decision, an invisible architecture shaping our daily comfort, our communication, our whole experience, often completely unnoticed.
Until it goes wrong.
Exactly. So what does this all mean? Well, the next time you walk into a building, listen. I mean, really listen. Can you now start to hear the design? Can you identify where the sound feels well controlled, where it flows nicely, or maybe where it's a bit chaotic, revealing perhaps a design oversight?
Start noticing the acoustics.
Yeah. Consider how that subtle manipulation of sound shapes your comfort, your ability to communicate, your overall experience in all the spaces you use, public and private. Once you start listening with this new understanding, you'll find buildings suddenly have a lot more to say.
You'll perceive the world around you with a richer, more critical ear.
Absolutely. A fascinating world to explore.